To be able to calculate the components of the weight on an inclined plane, let's draw a free body diagram. And on that free body diagram, we're going to draw the forces that are acting on this object. Okay, so the first thing I normally do is to mimic the inclined plane. Okay, and then I'm going to have my object here. So there's the object, there's that box there. And the first force we normally draw is the force going vertically down, which is the force of gravity. Okay, and if I imagine that this is the horizontal axis, the force of gravity is always perpendicular to the horizontal. Okay, this angle here is the same angle there, that's angle theta. This angle here is going to be 90 minus theta. Let's just make sure that it's clear. It's 90 minus theta. Now, there is a force that always acts perpendicular to a surface. Because the object is pushing the surface will push back. That force, we call it a normal force, Fn. Now the normal force pushes upwards, but it's going to be balanced by another force that acts perpendicular but in the opposite direction. We're going to call that force weight perpendicular. Why are we calling it the weight perpendicular? It's because it's at a right angles to the surface, so it's called weight perpendicular. Okay, then you notice there's an object that pulls the object downwards on the slope. Okay, the force of gravity has got an effect along that slope, and we're going to call that force Fg parallel. Okay, now I've got two perpendicular components that are acting, Fg parallel and Fg perpendicular. These components of the weight are perpendicular to each other, meaning I can construct a parallelogram out of this diagram by simply drawing another component that is parallel to Fg going this way, and then another component that is parallel to Fg parallel going that way. So I've completed a parallelogram. If this is a parallelogram, I know that opposite sides are equal and parallel. Okay, so this side here is also Fg parallel. This side here is also Fg perpendicular. Now, doing some bit of geometry of angles, this is a right angle. Okay, Fg parallel and Fg perpendicular at right angle to each other. If this angle here is already 90 minus theta, what is this angle going to be? It's a complementary angle, so this angle must be equal to theta. Okay, so 90 minus theta plus theta gives you 90 degrees. Fair enough. So to calculate Fg parallel and Fg perpendicular, which is what we want, the components of the weight on an inclined plane, we're going to use the trig ratios. Let's start with Fg parallel. Here is Fg parallel, there is Fg, and there is Fg perpendicular. So this angle here is 90 degrees, that angle there is 90 degrees. Fg is the hypotenuse, Fg perpendicular is the adjacent side, and Fg parallel is the opposite side. So I'm going to say Fg parallel over Fg is equal to the sine of theta. Then I'm going to have Fg parallel is equal to Fg times the sine of theta. Similarly, if I have Fg perpendicular over Fg is equal to the cos of theta, adjacent over hypotenuse. For the sine was opposite of hypotenuse, we can see that. Therefore, Fg perpendicular is equal to Fg times the cos of theta. So that is how I can easily calculate the components of the weight on an inclined plane. Remember, these components are parallel to each other, and whenever you deal with parallel components, one of them is always a sine, one of them is always a cos. So you need to quickly figure out which one are you going to use for the cos, which one are you going to use for the sine. It always helps to draw a free body diagram like this and show the components that are parallel, and then work out the components. But you don't have to do all this proof when you're performing a calculation. We don't need this proof. You can just start right here. You can just start right there and just say FG parallel is equal to FG sine theta, FG perpendicular is equal to FG cos theta. Okay guys, it's time to do some practice questions. My 5 minutes is up, obviously. Stick around, don't disappear. Practice makes perfect. At this stage, it's practice time. Calculating the components of the weight on an inclined plane. Question 1. Calculate the parallel and perpendicular components of the block in the diagram below. Question 2. An object of mass 30 kg pulled up an inclined plane by a force of 160 newtons. So the angle of inclination there is 18.5 degrees. The 160 force is acting parallel to the incline. The frictional force acting is 16 newtons. 2.1. Draw a free body diagram showing all the forces acting on the block. 2.2. Calculate the acceleration of the block. 2.3. The block starts from rest at the bottom of the incline and takes 3.5 seconds to reach the top. Calculate the length of the incline. So at this point, pause the video, practice time. Once you've done, we can continue with the calculation. I'm going to make an assumption that you guys have paused the video and we are good to go. So for question 1, let's mimic the incline again. We're going to say there's the object, there's the inclination. The weight is going vertically down, but we're not going to include it now. Okay, what we're going to get now is the weight perpendicular going in that direction and the weight parallel going in that direction. If there is friction, it will be going in the opposite direction of motion. So we already know that to calculate weight parallel is the same as weight times the sine of theta. The mass of the object is 40 kgs. Fg is equal to mg always. The weight is mass times gravitational acceleration, so it's 40 times 9.8 times the sine of 20 degrees. So here you now need a calculator. 40 times 9.8 times the sine of 20 degrees, you get 134.07 newtons. The 134.07 newtons is down the incline. Always, FG parallel is always down the incline. Now we need to calculate FG perpendicular. FG perpendicular, we said, is FG times the cos of theta, which is 40 times 9.8 times the cos of 20 degrees, and we're going to get a calculator again. 40 times 9.8 times the cos of 20, 368.36 368.36 newtons perpendicular to the slope. That is how you can calculate the parallel and perpendicular components. All you have to do is use those formulas: FG parallel equals FG sine theta, and FG perpendicular equals FG cos theta.
Moving on to 2.1, we are asked to draw a free body diagram showing all the forces acting on the block. Again, we're going to mimic the incline, and then we're going to place the object on the incline. What are the forces that are acting? Well, the first force we have is the weight. Now, I've got two options that I can draw. I can draw two kinds of free body diagrams. Okay, I'm going to show those two kinds. The first type is the one that doesn't have components. So I'll have the weight, Fg, acting downwards. Then I'll have the 160 Newton force going up the incline. Then I'll have the 30 Newtons and the 60 Newtons friction pulling the object down. So this is option 1. Okay, and then I'll also have one last force, normal force, always acting perpendicular to the surface. Okay, so I got 4 forces. The other alternative diagram, which is the one that I actually encourage learners to draw, because it is a working diagram. What does that mean? It is a diagram that shows you the components and how they are acting. So first draw the weight parallel, which is I'm drawing the components with a broken line. Then I can draw the weight perpendicular. So the weight that I could have drawn here, in this other diagram I'm drawing it as components. Then the other forces do not change. For example, I'm going to have a frictional force, and then I'm going to have the 160 Newton force, and then I'm going to have the perpendicular normal force. Okay, just gonna adjust the length of the weight perpendicular. It looks slightly bigger than the normal force. Okay. The second diagram has tremendous advantages over the first diagram because it helps me to see along the incline which are the forces responsible for motion. That's the advantage. The perpendicular forces, they are balancing each other out. They are balanced forces. So there is no resultant along the perpendicular direction. That's why the object moves along the incline. So the forces that are important or that affect the motion, I can now see whenever I draw a component diagram. There are 3 of them. There is the Fg parallel, there is the friction, and there is the 160 Newton force. These are the 2 forces. They are not involved in the motion of the object as it moves along the incline. So that is why I encourage learners to draw diagram 2, the component diagram. It is a working diagram. It helps you see the calculation. Okay, now we are asked to calculate the acceleration of the block. I'm going to use the component diagram because it allows me to see what's happening. Okay. Given a choice, I encourage you to draw that diagram. Okay, so to calculate the acceleration of the block, we're going to use Newton's second law, which says F net is equal to ma. Right. So F net is the vector sum of all the forces that are acting. We've already discovered that we can leave the Fn and the Fg perpendicular. They're acting at 90 degrees to the motion. They will have no components in this direction. So the forces that affect the motion that comprise this F net are those three forces that we've already ticked. So we're going to have Fg parallel plus F friction plus the 160, which we also call the applied force. All that is equal to 30 of A. The frictional force, you already know that it's 30 newtons, but for now let's leave it like that. Another important thing that we quickly have to decipher whenever we're dealing with the net force is which is the positive direction and which is the negative direction. Remember, we're adding force vectors, so it's important that we quickly identify the positive direction and the negative direction. It's always a good practice to make the direction of motion the positive. So in that case, that is why I've already made the 160 Newton positive. Now on the side I need to calculate what Fg parallel is. It's Fg times the sine of theta. Fg is going to be m times g, 30 times 9,8 times the sine of 18,5 degrees. This will give me 93,288 newtons. Now remember, this 93,288 newtons is going to be negative. The friction is going to be negative. Only the 160 Newton force is positive. So a negative 93,28 plus negative 16 friction plus 160 is equal to 30 times A. Okay, so now we need to do the math on the left hand side. Add all those forces, but bearing in mind that some of those forces are negative and some of those forces are positive. So here I end up with 50,712 is equal to 30 of A. Right? I can now remove this. We've already seen. Sometimes it's better to do the calculation for Fg parallel on the side. Avoid entangling this. Okay? So now I can work out what A is by dividing both sides by 30. So if I divide 50,712 by 30, I get 1,69 meters per square second is equal to A, and this acceleration is up the incline. So the acceleration here is 1,69 meters per square second. I'm going to need this value. Since I've got limited space, I will need that acceleration value again. Okay. Next, the block starts from a rest position. Okay, it's another keyword that we always need to be aware of. A rest position simply means the initial speed of this box is naught. So the initial velocity is 0, and it takes 3,5 seconds. Alright, to travel that. Our acceleration value, we already know it's 1,69. Now we want the length of this incline. So here we can now employ an equation of motion which says delta x is becomes VI delta T plus half A delta T squared. Alternatively, some prefer to use S equals UT plus half AT squared. Same thing. So, we know the initial velocity is 0. So this first expression becomes 0 plus a half times 1,69 times 3,5 squared. Remember, whenever you're employing an equation of motion, the idea is to get three quantities. Then the fourth quantity that you want to work out, you're going to choose an equation of motion for it. So you're now going to have to choose an equation that has got 1, 2, 3, 4 quantities from the big four. Remember the big four equations of motion? Yeah. From those big four, I generally call them the big four. So choose one of the big four to solve the problem. In this case, we chose the one that says delta x equals VI delta T plus half A delta T squared. So from here now, we now need to use our calculator to get the answer. So the answer becomes 10,35 meters. That's how long this incline is. Okay. Thank you guys for watching. I hope you now understand how to calculate the components of the weight. We call them the parallel component and the perpendicular component. One of them you use sine theta, one of them you use cos theta. The parallel component you use FG. Parallel is equal to FG times sine theta. The perpendicular component use FG. Perpendicular is equal to FG times cos theta.